Laplace transforms. The definition of a Laplace transform is the Laplace transform of a function little f is equal to the integral from 0 to infinity e to the minus st times the function you're transforming, dt. We're integrating out the time variable, let's say t is our time variable, t is the independent variable. So after we do this integration in the definition, we can see that there will be no more t's left, only s's. S's will be our new variable. Here's the plan then. This is a transform that takes a function in the regular world where our independent variable is time and our dependent variable are little y's or little f's. We take the transform of our problem, a transform of a function, a transform of something, the Laplace transform of whatever, move it into the Laplace world when we take the transform. There are no t's in the Laplace world. All of the independent variables in the Laplace world are s's, and all the dependent variables are capital letters by our convention. So the Laplace of little y is equal to big Y. This would be little y of t, and that would be a big Y of s, a function of s. What's s? I'm going to be super vague about that through this first video. We'll talk about it later. Right now I'm going to be super vague, and s will be how we need it to be. We'll see what that means in a minute. Anyway, it's an integral transform. We take the transform of any function by popping it into this definition and doing this integral, this improper integral. So it's an integral transform, so it has all the properties of regular integration. If I take the transform of the sum of two functions, I want this to be the transform of the sum of the transforms. Let's pop this into the definition then. Taking the transform of anything means I'm taking the transform of f1 plus f2. So there it is. Taking the transform. All I have to do is do that integration. Well, of course, what I'm going to end up doing then is distributing that integral across this plus sign, and I can see that I'm going to get I see that I'm going to get then the transform of f plus f1 plus the transform of f2, and that's then going to be the transform of function 1 plus the transform of function 2. So that sort of works just like you think it would work. If I take the transform of a sum, it's the sum of the transforms. Also, a constant can come outside. So what I'm trying to prove here is that the transform of c times a function is just equal to c times the transform of that function. Well, that makes sense, because if I were to take my transform of a function, the transform of anything is just pop it in here, so there would be a c, and it's a constant, and this definition is just a regular integration. So I know that with an integration I can take a constant outside. So this piece here then, the square bracketed piece, is just by definition the transform of little f, which I could write as big F of s, not times f, but of s. We've integrated out the t. So even without me saying these two linear properties, you would probably have assumed that these things are valid anyway, but now we've officially shown them, so we can use them. But we haven't transformed any actual functions yet. What have we done? We said that the transform of a function of t becomes a function of s. Our convention is that if you transform a lowercase letter, it becomes an uppercase letter, so we can keep track of what's in the Laplace world and what's in the regular world. And we've we've used the linear properties of an integral to have our linear properties of this integral transform, this Laplace transform. But let's actually transform a function. All right, let's start on something easy then, just a constant. I want to transform 2. So really all I'm doing is taking the definition, and the definition is the transform of f, integrate from 0 to infinity e to the minus st times the function dt. And since the function I'm transforming is 2, I just have to do this integration. Now, it's an improper integral, so we should be setting this up where we replace this infinity with an a, do all my integration, and then take the limit as a goes to infinity. For now, let's just do this in a more casual way. We're going to integrate this function. I'm integrating this function with respect to t, so s is a constant. There's my integral with respect to, integrate with respect to t. And now I have to sub in the top minus sub in the bottom. And those sub-ins are, so sub in the top, that sub-in is infinity on the top and 0 on the bottom. So when I sub, here's where when I sub in infinity, I'm going to write this in a casual way so that we can just sort of see what's going on. I'm subbing in infinity 4 times. So that's e to the minus s times infinity, 2 in the minus s, minus, when I sub in 0, that's going to be, when I sub in 0, 4t, e to the, I'll put it in there, but e to the s times 0 is 1. So it's sub in the top minus sub in the bottom. All right, simplify this. E to the 0 is 1, so this whole piece disappears. That minus sign and that minus sign are going to cancel, so that's a plus, and that disappears. I get 2 over s. What's this e to the minus s times infinity? Well, e to the minus infinity will be 0. So I'm making e to the minus infinity, I'm making this piece equal to 0. I'm thinking about as t approaches the limit, as t approaches infinity, this e to the minus s times infinity goes to 0, and that gets rid of this whole piece. That turns this whole piece into 0. I'm going to delete it. Now, just by pushing the delete button, I made the assumption that s was a positive number, right? Because if s was a negative number, then this would be e to the minus a minus infinity plus e to, that would go to infinity. So how do I know that s is a negative number? Well, it is or it isn't. If it isn't, then this whole chunk of algebra goes to infinity, and the transform of even the simplest function isn't good for me. So we're going to make the assumption then, so that this is useful, we're going to make the assumption that s is greater than 0 in this case. So s, we're going to assume that s is a positive number, so this highlighted piece then is 0. Which means that the Laplace transform of 2 is 2 over s. So we can take, I never have to do this integration again. If someone, well, in fact, I can maybe even generalize this a little bit further. The 2 didn't do anything, right? If the 2 was a 7, this would have been 7 over s. So we can make this a rule. The Laplace transform of a constant, let's say k is a constant, is just k over s. We can make that a rule. That's what we're going to do in the end. If you take a look at your Laplace transform chart, there's a chart provided in differential equations books. You can Google Laplace transform chart. There's a PDF of the Laplace transform chart online here. But the Laplace transform chart is basically an integration chart where this Laplace definition, this integral definition of a Laplace transform, is the integration that this chart is doing. So if I need to Laplace transform a constant, it's just a constant over s. So if someone said, oh, what's the Laplace transform of y equals 8, this constant function y equals 8, I would say, oh, it's 8 over s. Backwards, though, taking the inverse Laplace, undoing the Laplace, getting out of the Laplace world, getting back into the real world. If someone says, oh, the Laplace function, the capital F, is equal to 11 over s, what's the function that would have transformed into 11 over s? I can say, oh, that's 11. We can take the inverse Laplace transform. The inverse Laplace transform of 11 over s is 11. That 11 is in the real world where our independent variable is time, t, and the 11 over s, its transform, is in the Laplace world where the independent variable is s. So now we can transform a constant. What about taking the transform? Okay, we can transform a 0th order polynomial, a constant. Let's try transforming a first order polynomial, y equals t, to see what happens. Let's take the transform of y equals t. If I'm taking the transform of y equals t, notice I'm doing the same thing. I'm copying and pasting that definition because that's how you take the transform. You take the transform of a function by integrating from 0 to infinity e to the minus st times that function. Now here I'm going to have to do integration by parts to do this integration. So in the integration by parts, I need one piece to differentiate. Here's where I got to think about notation. Some people do integration by parts with f and g prime. Some people do integration by parts with u and v prime. It's whatever you're comfortable with. I'm going to use f and g prime because that's what I'm comfortable with. So I would set f equal to t. That's the f from parts, not the f from, that's the f from parts, not the f from that I'm transforming up here, the f for the Laplace transform. So this little square down here, also g prime then, is going to equal to the e to the minus st. These f's and g's are just for me doing parts so I can do this integration. So I also need f prime, which is going to be 1, and I need g, which is going to be integrate with respect to s. So that would be, oh no, integrate with respect to t. So there's a minus s on the front back. So there's my this part here, those two lines, that's my integration by parts. So I can put this in, that's going to equal to f times g minus the integral of the two things I made. So minus the integral of the two things I made, which would be the 1 times the g dt. And I still need here then, this has got to go from 0 to infinity after those two pieces. So now I need to do this integration. Again, these are all improper integrals, and I'm not doing them the way with the, replace the infinity with a. It's a little sloppy, but for brevity, we're doing it this way. Now, sub in the infinity minus sub in the 0 for this part. When I sub in the infinity for time, that's going to be infinity there, infinity there. Infinity times 0, we've already established that s is going to be a positive number in this case. Minus, when I sub in the 0 for time into this piece, that whole thing is just going to be 0 times e to the 0. So there's my sub in the top. I still need to do this integration. But let's take care of this right now. What's infinity times e to the minus infinity? Infinity times 0. Well, we could do L'Hopital's rule. The thing is that t the first function is just linear, whereas e to the minus st is exponential. You could do L'Hopital's, e to the minus st is a stronger function. This whole piece goes to 0. So our integral is just this, our transform then is just this piece. I still have to do this integration with respect to t. So let's do it. That's going to be another s on the bottom, and I still have to go sub in the top minus sub in the bottom. Now let's make sure that I get my minuses okay. You have them okay. When I sub in the top, well, every time I sub in infinity, I'm getting 0. Same argument. Minus sub in the bottom, which is my minus 1 over s squared. All right, long story short then, the Laplace transform of t is equal to 1 over s squared. So now I can transform any line using the Laplace transform of t rule, our Laplace transform of a constant rule, and our idea here that the Laplace of a sum is the sum of the transforms, and the transform of a constant multiple is just a constant multiple of transform. As an example, let's take the Laplace transform of a general line. So a general line would be some mt plus some constant. So t is our variable. So instead of mx plus b, I'm doing mt plus b. I'm taking the transform of that line. Well, that would be equal to, m is a constant, so I can bring that out, the Laplace transform m times the Laplace transform of t plus the Laplace transform of constant is equal to m times the Laplace transform of t I already have, plus the Laplace transform of a constant we already said was going to be a constant over s, so that'll just be b over s. So there, now we can take the Laplace transform of any line using the rules that we made. That will be the case. The more rules we have made, the less actual integration we have to do, the more that we can just rely upon combining the Laplace transform rules together. We can also, I guess, then inverse Laplace here, right? If I saw, let's do an inverse Laplace. So to write it as an inverse Laplace, I'm undoing. So the notation is going to be take the inverse Laplace of, and now this should be something with s's. So I'm going to go 7, let's say 7 over s squared plus 3 over s, and I'm going to say take the inverse Laplace of that, or what function would have transformed to this. Well, I can recognize then that this is just a line. This would be the inverse transform also transforms across. So that's the inverse transform of those two pieces. And what would have transformed to be 7 over s squared? Well, that would be 7t. What would have transformed to be 3 over s? That would have been 3. So I know that if the function that I see in the Laplace world, the function of s, was equal to, if the function in the Laplace world was equal to seven over s squared plus 3 over s, I could take the inverse Laplace of that and figure out what the original function was. either little f of t or y of t, whatever notation I'm using. So we can take the inverse Laplace of that. All right, so now what can we do? We can transform, with all our rules here, up to this point, we can transform any line. Let's see what the transform of an exponential function is, e to the at. If I'm transforming e to the at, again, I'm going up to this definition. It's a straight copy-paste, and I'm transforming e to the at. So I'm taking the transform of e to the at, I'm taking the transform of e to the at. Well, in this case, they're both e to the. I can do common basis, e, add the exponents. So this can be made as up top plus at, common basis, add the exponents, and if I factor out the t here, if I factor out the t, that'll be a minus. Now I can just straight integrate this. Because s is a constant. Well, s is a constant with respect to t. Remember, I'm integrating with respect to t. I'm in the real world. And I still have to go sub in the top minus sub in the bottom. Those are t's. Now when I sub in, so there's my integration. When I sub in for infinity, I'm going to make the assumption that s is bigger than a, so that minus s minus a, so that this exponent then is negative, and when I sub in the infinity, that'll be e to the minus infinity, and that'll be 0. Minus, when I sub in the 0, I'm going to get e to the 0, that's a 1 over minus s minus a, which cleans up to be 1 over s minus a. So what did we just prove? We proved that the Laplace transform of e to the at is equal to 1 over s minus a. That's what we just proved. And we don't have to do that integration again unless someone asks me to do it. And also, we can do things like, say someone says that in the Laplace world, so capital F of s, we're in the Laplace world, someone's telling me that the Laplace of a function happens to be equal to, I don't know, how about 6 over s minus, or 6 over s plus 3. Then I can see that f of t must be equal to, okay, it's 1 over, so that 6 is just a constant. If I'm matching s minus, or s plus 3 to s minus a, the a must be minus 3, so this would be e to the minus 3t. So we can take the inverse transforms using this definition as well. All right, stop for a second. At this point in Laplace transforms, there's a potential to lose focus. What are we trying to do? Why am I learning Laplace transforms? What is the point of this Laplace transform idea? Well, the point of this Laplace transform idea is to solve differential equations. And one of the beauties, or why this works, is in the Laplace world, there are no derivatives. In the Laplace world, there are no derivatives. So that means if I've got a differential equation problem and I take the Laplace transform of it, I move it into the Laplace world. No more t's, all my variables are s's. When I move it into the Laplace world, there are no derivatives in the Laplace world. So now there was a y prime here, of some function I don't know, I move it into the Laplace world, and there are no derivatives, there's no more y primes, there's no more primes. My solving of the differential equation is done for me. All I have to do is then move it back out of the Laplace world and back into the real world, and it pops out in the real world already solved. That's going to be the plan. I guess the next thing I need to do then is justify my statement there are no derivatives in the Laplace transform world. Why is that? Well, let's see. Let's take the Laplace transform of the derivative of a function. Let's take the Laplace transform of y prime. Now, I'm saying it's s times the Laplace transform of y minus y naught. Y naught's a constant. But let's prove that. Anything that has to do with a proof, I'm going to go back and start with my definition. But now I'm taking the Laplace transform of y prime. Now, this has got to work in general for any y, for an unknown y. I don't know what y is. So how am I going to do this? I'm going to do this with parts again. So I need a function to differentiate. Well, the function I'm going to differentiate is this e to the minus st. And I need a function to integrate. The function that I'm going to integrate is the y prime, because I can integrate that and it's just y. I can say that, you know, the integral of y prime is y even without knowing what actually y is, what the real function of y is. So I'm going to have f prime is equal to minus s. I'm differentiating with respect to t here, and g is equal to y. So when I put these two pieces in, it's going to be f times g, f times g, minus the integral of the two things I made. So minus the integral of the two things I made. I made e to the minus st, so there's a minus s here. There's the f. There's the, oh, and so there's, from this step to here is integration by parts. Now, we go sub in the top minus sub in the bottom into this piece. We're subbing in for infinity. So, subbing in t equal to infinity. Those are t's. So that's going to be an infinity, and for that t, we're going to do the same thing. That's going to be 0. Oh, wait, but this y is a function of t. So, it's y of infinity, or the limit, minus, when I plug 0 in to this, I'm getting e to the 0, that's 1, and y of 0. So this is this. And I still have this minus the integral piece here. Let's take this minus s to the outside. Now, e to the minus infinity and y to the infinity. E to the minus s is going to be a stronger function, assuming that this y function is not an exponential of an exponential. So this whole piece becomes 0 when I sub infinity in. So I get 0 minus, well, what's y of 0? Well, that's my initial condition. That's going to be given in the differential equation problem. That's y naught. That's the initial condition. And this is plus s times, what is that? Well, that highlighted piece, that's just a Laplace transform of y by definition. So we can call that then capital Y. The Laplace transform of little y is capital Y, our unknown function. And that proves that the Laplace transform of derivative is s times the Laplace transform of the undifferentiated function minus y naught. We've proven this rule. There are no derivatives left in the Laplace world. Okay, remember, what's the point of all this Laplace transforms? Well, there are no derivatives in the Laplace transform world. So, let's take a look. Here's a differential equation. If I Laplace the differential equation, that is, take the Laplace of both sides, I'll get rid of the derivative. So the plan is going to be this. Laplace the differential equation. That absorbs the initial condition, because the Laplace of y prime is s times the Laplace of y minus y naught. That absorbs the initial condition into the problem. So we're going to Laplace both sides of the differential equation. Then we're going to solve for capital Y. Capital Y is the Laplace of the little y of t, the unknown function, the function we don't know, the solution to this differential equation. After we've solved for capital Y, then we're going to unLaplace both sides, take the inverse of both sides, and then we'll have little y equals our solution. Let's see how this works. So step one, I'm going to take the Laplace of both sides of this equation. The Laplace of y prime, using our rule that we just made, the Laplace of y prime, the Laplace of the left-hand side of this would be s y minus 0. That's s times y minus y naught equals 2 times the Laplace of small y is capital Y minus the Laplace of 4, the Laplace of a constant, is 4 over s. So there's our step one. We took the Laplace of both sides. Now it's going to be solve for y. So I'm going to get s times capital Y minus 2 times capital Y is equal to minus 4 over s. I can factor that y out. And finally I get capital Y is equal to so now I've got capital Y equals. All I have to do then is unLaplace both sides of this. The capital Y is going to unLaplace to be little y of t, in other words the unknown function, the function I'm looking for. And I got to unLaplace this. I don't have anything, I don't know how to unLaplace this, so I'm going to break it into pieces. I'm going to use partial fractions to break this into pieces. So I skip some steps here, or I ask the machine to do it. But you can check. If I break that into partial fractions, then I get 2 over s minus 2 over s minus 2. Now I'm set. I can unLaplace this piece. That's just 2, because the Laplace of 2 would be 2 over s. I could unLaplace this piece. That would be 2. This 2. Let's move that 2 out to the front. That's 2 times the inverse Laplace of 1 over s minus 2. That would be, that's the rule we made up here, e to the 2t. So let's unLaplace both sides. I get little y of t is equal to 2 minus 2 e to the 2t. Also note to self, it does go through the initial condition. If I make t equal to 0, then I get 2 minus 2, 0. It does go through the initial condition, the origin. There's the solution to that differential equation. Now, yes, it's a first-order linear differential equation. We probably would have normally done this as a y prime plus py equals q. We're just illustrating the technique of Laplace.